Hello, welcome to the talk on software-based fault injection attacks against Intel SGX. I am Kit Murdoch. I'm a PhD student at the University of Birmingham. I want to begin by touching on trusted execution environments. So many of us now use personal computers which store a huge amount of private data and also private applications. Trusted execution environments were created out of a desire to protect that information and to protect it even from the operating system itself, so even from an attacker who may have root. Most manufacturers have their own version of a trusted execution environment, and later on we're going to be looking specifically at Intel SGX. There's one more thing I want to introduce before I get into our research. Dynamic voltage and frequency scaling. If you want your computer to go fast, it's going to get hot. And that's why we need voltage and frequency to be dynamic on modern computers. The frequency and voltage can be scaled up when required for computationally complex operations, and it can be scaled back down to protect the CPU from damage. And a lot of people use this DVFS to tweak their computers, and there's a huge number of apps to enable this. We've got CPU Tweaker, AMD Overdrive and Throttle Stop, and they're just a few I found. And the reason these apps can do this is because most manufacturers have created a way to modify the hardware through the software, and they use memory mapped registers. And these things come together in a new type of fault injection attack. Because when I say fault injection, this is what you think of. An attacker who has direct access to a microcontroller and a lot of specialised laboratory equipment. But not anymore. In 2017, Clockscrew created a new class of fault attacks. On an ARM processor, they caused faults and leveraged those faults on a Nexus 6 to infer a secret AES key that was stored within TrustZone, which is a T, and to trick TrustZone into loading a self-assigned application. In 2019, VoltJockey achieved very similar results, but this time looking at voltage. So now let's look at our research. We wanted to investigate undervolting in Intel CPUs. We specifically chose voltage because it gives us access to a higher level of granularity compared to frequency. The first thing we wanted to know was, is there a memory mapped register specifically for voltage? And yes, we found an undocumented MSR, model specific register, hex 150. This MSR can perform a large number of functions, but we're only interested in the under and overvolting. This is the layout of the MSR specifically for undervolting. Adrian Tang's PhD thesis documents in more detail the other functions, but a lot of this has been based on the reverse engineering efforts of Throttle Stop, which was written by Kevin Glynn. So how do we use this? Here's a little bit of code to undervolt. It's relatively straightforward. I haven't included the function to convert an undervoltage into the format required by the MSR, but that is available on my GitHub. So the first thing we wanted to do is just compare the idle voltage with the voltage when the computer crashes. And these were our results for different frequencies on an Intel Core i3. As you can see, for each frequency, there's a very large stable operating voltage. But we wanted to know, is it possible to fault it somewhere close to the crash point? And this is the code that we wrote. Our initial experimentation just looked at a single large multiplication in a loop. Theoretically, this loop should never exit. If it does, we will have observed a faulty result. We tested at all the available frequencies for our CPU. So let's have a look at how we did this. So we're running that single multiplication again and again, starting at minus 252 millivolts and reducing by 1 millivolt at a time. And there we've got a faulty result. And if you look at the XOR, you can see it's a single flipped bit. Now this was just one multiplication, so we ran it again, but just randomly generating our operands to see if we would get another faulty result. And again, with random numbers, we're getting the same flipped bit. So we repeated this many times. And there you can see, instead of one flip bit, we've got contiguous bit flips. So we plotted our results on a graph, and we found that frequencies in the middle of the CPU's available frequency range were much more stable. If you went to very low frequencies or very high frequencies, you were much more likely to get a crash than a fault. And for this particular i3 machine, we focused at 1 gigahertz as we found it to be the most stable. Now, it's all very well creating multiplication faults in user space, but you have to be root to control the voltage. When I introduced T's, I talked about them being safe even from an attacker who is root. And Intel's T is called SGX, Software Guard Extensions. Let's take a look at how that works. You have an untrusted or normal user space part of an application. It will create an enclave, and that will create a trusted portion which is encrypted. And this encryption is supported by hardware. When you call the trusted function, it will go through a call gate into the trusted portion, and you have to define what your inputs will be very carefully. The trusted portion will run, and when it returns, it will return to untrusted code. And the important part here is that the operating system has no direct access to this trusted part. It should protect against attacks, even from an attacker who has root. And there's a small region for the EPC, the enclave page cache, and that contains the code and the data, and that is encrypted. An EPC can only be allocated to one enclave. It's got integrity protection, and it can't be tampered with. The key is in the processor. So what happens if we have bit flips in the EPC? Well, the integrity check fails and it locks up the memory controller. Rowhammer doesn't work inside SGX because the integrity check fails. Back to looking at the frequency and voltage regulators, what we discover is that the voltage and frequency is going to be changing on the CPU core even when something is running inside SGX's trusted code. So let's look at what happens if we try and fault inside SGX whilst we're undervolting in user space. The right-hand side is user space and the left-hand side is enclave SGX multiplications. And as you can see, we've got a fault. And it's the same fault that we had in user space. We can bypass the SGX integrity check by inducing a fault whilst SGX is running computations. We obtained thousands of results from creating random multiplications, and we created a database. One of the things we decided to include after a little while was the operating temperature. We observed that slightly less undervolting was required on a hot day, for example. However, all our faults were obtained in normal ambient office temperatures. And we came to a few conclusions. The smallest first operand that we could fault was 89AF. The smallest second operand was 1. And the smallest cumulative result was hex 200000. We also found that the order mattered. We could fault this multiplication, but we couldn't fault that multiplication. Now at this point we'd only been testing with one machine, and we wanted to see if the results would occur across all CPUs. We tested everything on either Ubuntu 16.4 or 18.4 and everything on Linux either 4.15 or 4.18. One of the most interesting things we found was that we tried to buy an absolutely identical machine to our first testbed, and this was the result. As far as we could tell when we bought the i3, they were identical machines, and yet you can see that there's very different operating voltages there. However, we were still able to create faults, and the faults occurred in exactly the same way on both machines. The position of the flipped bits was identical. We continued testing with a huge range of computers, and all the way from Skylake up, we were able to fault everything we found. Our research up until this point had just been inducing faults into multiplications, and we believed that we should be able to leverage that into an attack. So we decided to go after RSA, and remember, this is all happening in calculations inside SGX. We started off by waiting for the multiplication faults, so waiting to get an error in a multiplication before doing a decryption, and then seeing if that decryption would also fault. And this is what happened. I'm undervolting at minus 239, and I'm doing a decryption. And as you can see, it's saying all fine, and that large hex you're seeing is the decryption. And there we go, we've got an RSA error. At minus 240 millivolts, we get an error. Now the interesting thing about the code that we used is that it was Intel's example code for RSA, and that implementation uses the Chinese remainder theorem optimization. And this is attackable using the Lenstra attack. And I think it's really interesting to note here that this is an attack from 1996, and it's being leveraged on a modern computer using a trusted execution environment that is basically cutting edge. The Lenstra attack requires a single fault in one of the two exponentiations, and it improves upon the Bell core attack